In this video, I'll teach you about the basic derivative rules and how to apply them. Previously, we talked about questions like this, where we're given a function, for example x squared plus 5x, and we're asked to use the limit definition of the derivative to compute f prime of 2. The limit definition of the derivative looks like this. F prime of 2 is the limit as h goes to 0 of f of 2 plus h minus f of 2 divided by h. So now we're going to use the definition of our function to simplify that fraction, and then think about what happens as h goes to 0. So f of x is x squared plus 5x, so f of 2 plus h is 2 plus h squared plus 5 times 2 plus h. So that's f of 2 plus h. F of 2 is 2 squared plus 5 times 2. And that's all divided by h. Okay, so we've got some algebra to do here on the top of our fraction. When we multiply out 2 plus h squared, remembering to FOIL, we get 4 plus 4h plus h squared. 5 times 2 plus h is 10 plus 5h. And then 2 squared plus 5 times 2, that works out to be 14. Still all divided by h. Now we can do some simplification. 4 plus 10 is 14, so the 4 and the 10 and the 14 cancel out. We can simplify again because 4h plus 5h is 9h, so we get 9h plus h squared, all divided by h. We can factor an h out of the top, cancel it with the h on the bottom, and we get 9 plus h. We're not quite done because we still have to think about this limit. So now we have to think about what's going to happen when h is 0. Well, when h is 0, 9 plus h is going to go to 9 as h goes to 0. And so that's the value of our derivative, is the number 9. So we've done that before. It's a little bit complicated. The algebra is messy, but it's a process that we've seen before. So what happens if we complete that long problem and we get to the very next problem and it says, hey, you've got the exact same function, x squared plus 5x, and now I want you to use the definition of the derivative to compute f prime of 3. You might throw up your hands in frustration and say, well, I'm going to have to do all that work again. There's nothing about the previous problem that helps us do this problem. This problem is going to be similar, but the answer to the previous problem doesn't really help us do this problem. So this will be another similarly lengthy problem. And what if we wanted the values of many derivatives? What if we wanted, remember the derivative represents the slope of the tangent line, so what if we wanted the slope of several different tangent lines to this function? Well, we don't want to have to go through that tedious process over and over and over again. We want some sort of way to get our answer more quickly. So what would be helpful would be for us to have a formula for f prime of x. So a formula that we could plug into that would tell us, no matter what value we wanted, the value of the derivative at that number. So it would tell us f prime of 2, f prime of 3, f prime of any number we would want. So how are we going to find such a formula? Well, we're going to do the exact same thing we did before, except instead of putting a number in the parentheses, we're going to leave it as f prime of x. Everything else stays the same. It's the limit as h goes to 0, f of x plus h minus f of x divided by h. So this is just like the previous problem that we did, except instead of putting in a 2, we're putting in an x. So the algebra is going to be even more difficult this time, but I think we'll be able to handle it. So let's see how this works out. So just like before, f of x is x squared plus 5x. So when I want f of x plus h, everywhere I see an x in my f formula, I'm going to replace it by an x plus h. So I get x plus h squared plus 5 times x plus h. And then minus f of x, that's just copy and paste our original function, x squared plus 5x. And now that's all divided by h. Okay, just like we had to FOIL out 2 plus h squared, we're going to have to FOIL x plus h squared. So let's go off on the side and do that. X plus h times x plus h works out to be x squared plus xh plus hx plus h squared. Xh and hx are the same thing, so that's 2xh plus h squared. So that goes on the top of our fraction here. So we've got x squared plus 2xh plus h squared. 5 times x plus h is 5x plus 5h minus x squared minus 5x, all divided by h. Okay, so this looks nightmarish, but we're going to be able to cancel some things out. So for example, we have a plus 5x and a minus 5x, so those cancel out. We have an x squared and a minus x squared, so those cancel out. And that's all we can do. So what do we have now? We've got 2xh plus h squared plus 5h all divided by h. We can factor an h out of the top. When we do that, we get 2x plus h plus 5 all divided by h. We can cancel out those h's, and we get 2x plus h plus 5. And just like before, we're almost done, but we still have to figure out what to do with this limit. What do we do as h goes to 0? But when we put in h equals 0, we get 2x plus 5. Again, that's as h goes to 0. And so 2x plus 5 is the formula that we were looking for. So 2x plus 5 is a formula that gives us the slope of the tangent line, that gives us the derivative for any value of x that we would want. And just to make sure, just to check from before, we want to make sure that f prime of 2 still works out to be what we want. So we're going to plug 2 into this new formula that we got, 2x plus 5, 2 times 2 plus 5. That really does give us 9, just like we got before. So this matches up with the answer that we got before, but this answer is way better because it allows us to compute the derivative no matter what value of x we want. Now, of course, you might be looking at this and thinking, holy moly, that's a lot of work to try to just get a formula for this derivative thing. Isn't there any easier way? Well, it turns out that there is. But before we get to those shortcuts, let's talk a little bit about notation. We've seen the prime notation, so if f of x is our original function, then f prime of x represents the derivative of that function. It represents the slope of the tangent line, the instantaneous rate of change at a given value of x. But we've got a couple different notations that you'll see in class and in the textbook. One is this dy dx notation. This is sometimes called Leibniz notation, named after one of the mathematicians who developed calculus. And then a variation of the Leibniz notation is d over dx, and then in parentheses, a function. So d over dx just means the derivative of f of x, the derivative of what's in the parentheses. So if you ever see d over dx and then something next to it, that just means the derivative of that thing. So dy dx just means the derivative of y. You can think of that y as being in parentheses as well. Okay, so let's get to those shortcuts. So the first shortcut is something called the power rule. So this tells us how do we take the derivative of a function raised to a power. And it tells us that what we do is we take that power, n, and bring it down and multiply it by x to the n minus 1. So we bring down the power and then subtract 1 from the power. So just to give you some examples, the derivative of x squared, in this case n is 2, so that would be 2 times x to the 2 minus 1. That's 2 times x to the first power, also known as just 2x. The derivative of x cubed would be 3 times x to the 3 minus 1. That's 3 times x squared. We can do some other powers as well. So for example, I could take the derivative of the square root of x. What you might remember from algebra is that we can rewrite this square root. A different way to write square root is with a fractional exponent. X to the 1/2 is just a different way to write the square root of x. So now 1/2 is my n, so I get 1/2 x to the 1/2 minus 1, 1/2 x to the negative 1/2. Now we can leave our answer as 1/2 x to the negative 1/2, but if we'd like to try to understand that function a little bit better, we can rewrite that by understanding what x to the minus 1/2 means. X to the 1/2 means square root, and that minus sign means 1 over. So this is 1/2 times 1 over the square root of x. And so those are two different ways that we could write the exact same answer. Another derivative rule is that the derivative of a constant is 0. And that constant can be anything. So the derivative of 17 is 0. The derivative of negative 1,000 is 0. The derivative of pi, remember pi is just 3.14 something something something, that's 0. The derivative of 6 to the 17th power, some gigantic number, is still 0. Pay special attention to this last example. Notice that it was 6 to the 17th power, not x to the 17th power. If it had been x to the 17th power, then we would have used our power rule that we learned on the previous slide. So because it was 6 to the 17th power, because it was a constant, this whole thing derivative is 0. So don't mix up the power rule with the constant rule. Every once in a while you'll see a tricky question like that, so don't get fooled. We've got some slightly more complicated derivative rules. This one's the constant multiple rule. Again, you don't want to get this one mixed up with the constant rule. This is saying when we have a constant times a function, not a constant by itself, but a constant times a function, the constant just sits there and doesn't do anything, and then we take the derivative of the function normally. So what this would mean is that if I wanted to take the derivative of, let's say, 5 times x cubed, 5 is my constant multiple, so that's my c here. And so what the constant multiple rule says is that this is just 5 times the derivative of x cubed. And we know the derivative of x cubed from before. We bring down the 3, subtract 1 from the power, so we get 3x squared. And then we would normally simplify this to get 15x squared. So that would be our final answer to this one. Let's do another example. Let's say we had the derivative of negative 4x. Well, negative 4 is my constant here, so that's just going to be negative 4 times the derivative of x. But what's the derivative of just x? Well, we have a power rule, so if we can think of just x as being x to a power, well, we can do that just by thinking of x as being x to the first power. X to the first power is just x. So the derivative of that would be 1 times x to the 0. But anything to the 0 power is 1, so that's negative 4 times 1, which is really just negative 4. So hopefully you're starting to see how these different rules that we're developing combine together, and we'll see many more examples as we go forward. All right, one more derivative rule for today, which is really just 2 derivative rules that work the same way. This we call the sum and difference rule. And it looks like 2 rules, but it's really just the same rule, one with a plus and one with a minus. And all this says is that if you've got 2 functions added together, you add the derivatives together. And if you've got 2 functions subtracted together, you subtract the derivatives. We'll see how this rule applies with our first example in the next slide. Okay, so let's do an example. Let's put all of our rules together and take the derivative of 5x cubed minus 7. The first thing we need to notice is that we've got a subtraction. It's 5x cubed minus 7. So what we need to use is the difference rule. The difference rule says that you take the 2 derivatives separately. 5x cubed minus 7. So whatever the derivative of 5x cubed is, minus whatever the derivative of 7 is. All right, what's the derivative of 5x cubed? Well, now we use the constant multiple rule. This is 5 times a function, 5 times the derivative of x cubed. We'll deal with the 7 in a minute. And we know that the derivative of x cubed is 3x squared. That's from the power rule. And so that gives us 15x squared. What's the derivative of 7? Well, 7 is a constant. It's a constant all by itself, and the derivative of any constant is 0. And subtracting 0 doesn't do anything, so that means our final answer really is the 15x squared. All right, let's do one more example. This one's a little bit more complicated. So we've got x over 3 minus the square root of x plus 5 over x. First things first, because of the sum and difference rule, this is 3 functions added and subtracted together, so we can take the derivative separately. So this is going to be the derivative of x over 3, whatever that is, minus the derivative of the square root of x, whatever that is, plus the derivative of 5 over x, whatever that is. So we've broken our problem down into 3 simpler problems. Okay, what do we do with x over 3? None of the rules that we've talked about tell us how to deal with fractions. But when we think about x over 3, we want to think of that as being like 1/3 times x. That's equivalent to x over 3. If it helps, think of x as being x over 1 there. So 1/3 times x over 1, that gives us x over 3, but now we've got 1/3 times x. So our derivative, 1/3 is a constant, so this is going to be 1/3 times the derivative of just x. And as we saw before, we can think of just x as being like x to the first power. So that's going to be 1 times x to the 0, and that whole thing just works out to be 1/3. Next up, we've got the derivative of the square root of x. And we saw one like this before. Remember that the square root of x is x to the 1/2. So the derivative of the square root of x is going to be 1/2 x to the minus 1/2. Where did that first minus sign come from? So this minus sign right here is this minus sign. So that minus sign stays with it. And so we get 1/2 x to the minus 1/2. We can leave it like that, or just as before, we can rewrite it as 1/2 times the square root of x, because x to the minus 1/2 means 1 over the square root of x. All right, finally, 5/x. Just like we did with x/3, we want to write that separately. So we're going to write that as 5 times 1/x. Here, 5 is a constant multiple, so this is going to give us 5 times the derivative of 1/x. So what do we do with the derivative of 1/x? Well, again, we don't really know how to deal with fractions. None of the rules that we talked about deal with fractions specifically. But we can rewrite 1/x as x to the minus 1. Again, remember from algebra that negative exponents mean that we have a fraction. So x to the minus 1 is just another way to write 1/x. So now we can use our power rule, which says that we bring down that -1. So we've got plus 5 times -1. And then we subtract 1 from -1. So it's -1 minus 1, which is -2. Got to be really careful with these negative numbers. So 5 times -1 is minus 5. And we can leave it as x to the minus 2, or we can realize that what x to the minus 2 means is 1/x squared. So if this were on a worksheet or on a problem in the book or on your online homework, that's how it would be written. So our final answer after all of that is 1/3 minus 1/2 square root of x minus 5 times 1/x squared. Or again, that could be written as 5/x squared as well. All of these things can be rewritten in various different ways. So just be aware that your answer might not look exactly like the answer on the back of a worksheet or in the back of the book. Now keep in mind that as we get better at taking derivatives, you're not going to have to write all of these steps all the time. You're going to get good at this, and you're going to get the practice so that you don't need to write every single step that I've written out here. This is just as we're getting started with this, while we're still learning the basics, just to show you step by step how I'm getting to the answer. Once you get the hang of it, feel free to skip steps and feel free to not have to write everything out so specifically like I am here. So rewatch this video if you need to, watch it a few times, kind of pause it, think about it, read through the book, look at some more examples, and let me know if you have any questions. We'll be going over examples of this in our next class, so take a look at those examples, again, read through the book, and try to understand this as best as you can. And if you have any questions, as I said, bring them to office hours, ask in class, but this is going to be what we're going to be working on next time.